Hello everybody and welcome to another week of CS202 Online, getting very close to the end. By the way, Wednesday is Veterans Day, so we will not have class, so that means that this is the last class before exam 2. So, what will we talk about today? Well, we will talk about the same thing we've been talking about for a little bit, and that is linked lists. So last time we left off the discussion by talking about the insert function into a linked list. So let's go ahead and pick up from there. But since it's been quite a bit of a weekend, let's go ahead and review what a linked list is. So a linked list is another way of storing data. We already learned about how to store it in arrays and vectors, which vectors are just arrays pretty much. And they're dynamically allocated arrays. And so the limitations or the pros and cons of an array is that it's very fast to access an array. That's the pro. You can just basically get any index and access it immediately. But the disadvantage is that it's not quite so simple to insert and delete things from the array, because you have to basically shrink or resize the array as you insert things, resize larger, or shrink if you delete, because if you just mark something as deleted, you're screwing up your access time and also wasting space. And so ultimately, I suppose that's one con that I didn't quite talk about last time. So with an array, you have to allocate a given size, and if you keep resizing every single time you insert, that's horrifying, because you gotta copy the entire array every single time. Makes things pretty slow. The linked list is going to basically flip the pros and cons around. So you're gonna have very fast insertion and deletion time, and you're gonna have slower access time because you don't have the way of accessing every index immediately. But another pro in the linked list that I didn't quite emphasize last time is the fact that you can allocate a node, and you'll see as I show you the insert function today, but you can allocate a node on the fly and insert it. So you don't need to have a fixed size in the data structure. So as you keep inserting things, it'll naturally grow as long as you have memory. So that in reality, you could say that as long as you have infinite amount of memory, you could infinitely keep inserting things into your linked list. Now, what does that mean in practice? In practice, it means that you don't have to think about what size to make something. You can just keep inserting and not have to worry about that. And it's only going to be using what you currently have inserted. It's not going to have extra space as you would in an array, where like you allocate an array of size 100, but currently you're only using 50 of that. And the other 50 is wasted, but you'd rather have it at 100 so you can quickly insert, right? So you can get around the issue with slow insertion in an array. And so that's one of the big pros actually of linked lists. Now, I have heard people, not even in this class, in Trio 2, which surprised me, say that, well, what about vectors? You can just insert whenever you want and not have to worry about the size. Well, you don't have to worry about it, but internally it's still an array. It still have a fixed size, and when you're doing pushback, it's inserting into that array of that fixed size, and if it runs out of space, it's going to make a newer array, and that's all happening behind the scenes. So to you, it's like, oh, okay, I can just insert as I want and then remove as I want and not really have to worry about allocating, so it must be magic. No, it's an array. It's just all happening behind the scenes. I mean, we did a vector class the other day, so that's pretty much how vectors are made, the vector class that we did maybe 2 weeks ago or a week ago. I don't even know. It's been quite a while now. Maybe, was it I think it was last Wednesday. It might have been last Monday. Well, not last Wednesday, because that would be last class, but the week before that. So anyways, the components of a linked list are, and we are talking about a singly linked list, is the data component and the next component, or the link component, which is the pointer that points to the next node in the chain or in the linked list. That's where the link part of list comes from, of linked list. So the data component can be actual data, like an integer or float, or it could be a template variable, but it can also be a pointer. It can give you a pointer to whatever you want. I mean, you could do an array actually inside of that pointer if you so were inclined to do so. You could do other linked lists in there. That was actually what the Inception assignment was that I gave a couple of semesters ago to 202 classes. You can check that out on YouTube if you're curious. But basically, if you've seen the movie Inception, there's different layers depending on where they're dreaming, the dream inside the dream and whatnot. So each linked list was like a dream layer. And so the deeper you went, it was like, take, the data component of the linked list was a pointer to another linked list, which could have a pointer to another linked list. So you had linked list inside of linked list. So linked list inception, basically. Pretty cool assignment. But what it really shows is that you are not constrained by what the data component is. You can make that a pointer to just anything you want. In fact, if you worked on the Creepio assignment, I could have actually used a linked list, I suppose, instead of a 2D array, although I don't see why I would. But in theory, I could have done that. And then in that assignment, I had a vector, pointers, as the third dimension, which I could have just as easily made the data component. So it's a lot of things you can do with a linked list. But the biggest advantage is you don't have to worry about the size. And you don't have to worry about moving things around when you insert, because it'll just throw it in and you're good to go. At the cost of access time, sure, but until you get to 302, this is going to be the best that you can do in that sense. And then from there, they talk about it. Well, if you take it with me, we'll talk about AVL trees and hashing and all these other things to try to keep the insertion and deletion fast, but also keep the access time fast. Because right now we're like this or this. We don't have like this. This is what we want. We want both things to be good, right? We can do this, and we could probably do both bad, but that's not useful. But in 302, we're going to slowly kind of push it up until we get here. So now we'll be hashing for the most part. But AVLs will be pretty much like very close. So anyways, as you can see, there's some code to a basic node in code. And we actually coded this, and we're going to pick up from that code. And then the important thing to emphasize is that when you're dealing with a linked list, things are not in order in memory. They can be pointing anywhere. That's why you can't really do quick access time, because you basically, it's like trying to get to follow the clues in a treasure map. They take you all over the place, not necessarily in a linear fashion or a nice little pattern. They could be like back and forth like this. It's like a treasure map where the first, think about like the movie National Treasure, right? Where like the first clue is like, I don't remember where, but let's say it's in LA. And then the second clue is like in Mount Rushmore. And then the third clue is like in Texas. And then you got to go all the way to Maine and then to like Alaska and then Hawaii. So it could be all over the place. Not necessarily like, oh, okay, let's take a road trip. And first clue's in LA. And then the next one's like in Arizona. And then like New Mexico. And then Texas. And finally Florida. It's not a pattern like that. It's like all over the place. So that is why access time is not ideal in a linked list. And by not ideal, I mean it's slow. You have to basically walk through the clues to get to the end of the list. But still, there are some data structures where we don't really need to traverse a linked list. Like when we talk about stacks and queues, we don't need to worry about that. And that just makes it ideal for using a linked list instead of using an array to still have the flexibility of insertion and deletion, which we care more about in certain data structures like stacks and queues, which, like I said, that's the last topic. That's the only thing we have left after we finish linked lists. So like a month from now is study week, I think. And then, actually, no, I think a month from now is the exam, the final exam. Check the calendars. But yeah, we're basically on the final stretch right now. We finished linked list, which we won't finish today. So the test will have some linked list material, but it'll, oh, actually, you know what? I said that this was the last time before the test, but technically speaking, I'll see you on Monday for the test, because we can do like a test review actually, because your test is on Tuesday. So yeah, I didn't think about that. So in theory, we could have an impromptu review session on Monday. So yeah, but anyways, test is on Tuesday next week. So, and check Canvas for details. But essentially after this, the test will have yeah, so I mean, we'll see. Depends, because the thing is, like, I try to upload it, but like I will only be able to upload it at like night. So it has to be like people have to come to the live review, otherwise that's pointless. I mean, they can watch on Twitch like last test, right? Because the last time we did a review was like literally at 24 hours before the test. So the best thing was for people to watch it on Twitch, because it takes me like maybe 5 hours to get things uploaded. The good thing is that I am giving my 302 test on Monday, so I don't have a class at 4, which means that I can upload like immediately after class and not have to like wait to not screw up the bandwidth for the other class. So anyways, we'll figure that out. But yeah, if you guys want a review, we can do a quick review. But anyways, the point is that the test will have some linked list stuff, some introductory linked list stuff, not very advanced. But after the test, we will continue talking about linked lists. We will talk about doubly linked lists, and then we'll do stacks and queues, and then we'll be done. If we have more time, we'll do reviews or bonus random stuff. But I don't think we'll have more time. I don't think we'll have extra time because stacks and queues can take a while. Like I can teach it really fast, but I can also go in depth. And if I go in depth, we can definitely use the time so that you're strong in those. Wow, 3 months. That's cool. All right, but anyways, 3 months. That means you're taking like, how many months of the semester we have? Let's see, September, October, November. Oh, okay, yeah, that makes sense. It's cool. Probably the summer too, maybe. All right. So, anyways, look forward to the potential review on Monday next week at 1 p.m. So for now, though, actually, there's really nothing I need to write here, but we just gotta go straight to the code. Actually, I know what I can do. Let's talk about a little bit about insert. So the test was originally going to be tomorrow, on Thursday, but here's the problem. Veterans Day is on Wednesday. And so because of that, the classes that have the test on Wednesday scheduled can't give it that day. So they would have to give it like today or on Monday. And that would have been a big gap between the tests, which encourages people to potentially cheat because we are using the pool of questions where we are all, even though the test should in theory be different because the pool just takes questions from the pool and the pool's pretty big. So every person's test is potentially different. You know, it's still open to potential sketchy stuff happening, right? And so what we announced on campus some time ago was that it's better to push it to Monday, Tuesday. And that also, again, gives us the opportunity that we can actually have a review on Monday. Whereas on Wednesday, we wouldn't be able to do a stream because it's Veterans Day. And, you know, it's like bad. Like, even if I wanted to, like, I'm not going anywhere. I mean, like, where am I going to go? It's like buyer season out there. But I can't technically do it because of rules. So I can't stream on Wednesday. So you wouldn't have a review. So it's actually good for you guys because you can have that review day. So, yeah. But, yes, check on Canvas. And, again, to reemphasize, the test is next Tuesday at 1 p.m. And the reason we picked that time is because it's the time on Canvas when the course was listed originally. So people who like might have requested off of work and things like that, they requested it for that, you know, time. And otherwise we start getting into the conflict of like, well, I can't make this time and I can make that time. But yeah, I'll still put like, you know, start at like 12:45 and then like 2:15 or 2:30 or something. But so you have a little buffer before and after, but you want to make sure you're planning for that. I did have one person of the full class. I had one person, I think, in each class. In my 302 and then in my... Actually, no, I don't think I was in my 302. I think it was just one person in 202 this time around that could not make the test. And they forgot, I guess. I don't know what happened. But I was like, well, I can't do anything about that. So, yes, I'll probably send you guys a reminder over the weekend. As we get closer, and also maybe on Monday as well. Okay, so anyways, insertion. So this, you know, I did a video of this over the summer, and what I'm going to do this time around to make it different than that is we're actually going to make each of these to be their own function. Maybe not the first one, but these bottom three, they're going to be each individual function. And the advantage of doing that is that I think it'll make the code more readable and easier to follow along than, because usually this insert function ends up being, well, I would say a lot, but in reality it's like 20 lines of code, which is not a lot in perspective, but it's a lot for like thinking logic. So we'll give that a try. We're basically going to split this function into tiny little functions, okay? So anyways, let's imagine the 4 scenarios. And that what also helps with that is that when we do a sorted linked list, which is a list that automatically sorts itself as you insert things into it, then we'll actually be able to use a lot of this code to apply it to that. So anyways, what we're trying to do is we're trying to make some insert functions so that we can insert in the linked list. And there are really 4 scenarios that you have to worry about when you're inserting into a linked list. The most easy and obvious scenario is when the list is completely empty. And what does that mean to be empty? Well, the linked list has one pointer in it, and that keeps track of the list, right? And that's called the head pointer. There can be also a tail pointer that points to the last thing. We're not going to worry about that right now. We can go in and add that later on. I want to make the simplest version of a linked list first, so we can make sure that we understand that before we start making it fancy, adding tail pointer, making it a doubly linked list, making it a sorted linked list. There's a lot of things we can do to make this more complicated and cooler. But I think the more basic we go, the less chance of getting confused with this stuff. And I'm assuming you will have an assignment on linked lists, so you can expect that at some point. So anyways, the first and most basic idea of inserting, and by the way, it doesn't really apply when you think about it to arrays, right? Because when you're thinking about arrays, you either have an array or you don't. There's no such thing as like an empty array. I mean, there could be, but like, that means you've already created the array. So even when I'm saying empty here, I'm saying like there's nothing exists in the list, right? In an array, if you're inserting in the middle, what you do is you copy the first part of the array into a new array, put the thing that you're inserting, and then copy the second part of the array or append it at the end, right? So that's how you would kind of think about inserting into like an array. Deleting into the array would be like the backwards of that. You basically just take something out and then copy over into a smaller array, or copy the end of the array back by one to fill the spot. And we did this when we did the Victor class. So you got to think about all these special scenarios when you're doing these things. So that's why we have all these fancy scenarios for simply just inserting something into the array, because we want to consider all cases. And that's, by the way, it's a very good practice to do whenever you're coding. You want to consider all cases, but take special emphasis on the edge cases, which are typically code that is like you normally wouldn't run into, but like when things line up in a blue moon or whatever, and they do that, and then if you don't consider that special case, the whole thing explodes, right? So, and there's been scenarios of this in history, so like all over the place. So anyways, the four cases here are inserting into a linked list that is completely empty. There's nothing there. There has never been anything there. That's one scenario. That's the first one. The next three scenarios mean that there is already something in the linked list. And by that I'm saying there's other nodes in the linked list. Doesn't matter if there's one node, 5 nodes, 100 nodes. It doesn't matter. They all fall into the same categories. And those are inserting at the beginning of a linked list, which means the first number in the list. But again, there's already something in the list, right? So we're gonna put it in the beginning. The other scenario is completely the other side of the list, appending something to the list at the end of it. So there's already the list. It could be just one item or 100, but you're trying to put something at the next spot at the list, right? So all the way to the end. So kind of drawn here. This is if we have this list right here, appending at the end would be basically making a brand new pointer here, like that. Boom, done. Alternatively, inserting at the beginning of the list would be if we have already a list going, like this. And then you have your head pointer, which points to the first item. And what we're going to do is we're going to make a brand new node. We're going to put it at the beginning, which means the head pointer is now going to be pointing to the brand new node we just created. And the next pointer here is going to point to whatever the old pointer was pointing to. And this logic that I'm saying, I'm going to go very slow on, because we really have to make sure we understand that. And I might actually do that in running now that I think about it. But first, let's go over the last example that we can have, and that's inserting in the middle. By middle, I'm saying there has to be at least one node before what you're inserting and at least one node after what you're inserting. That's the trickiest case because you're trying to basically sandwich it in between. And as you see when we're traversing a linked list, which means actually moving along the list, you have to kind of keep track of the one before. So that is, of course, the scenario that I drew here last class. So we have two things. Before they were like connected like this, what we did is we took that pointer off and then we basically linked it to the back of the new node, and the new node points to the old next node per se. Okay, so let's talk a little bit about some of this logic. Okay, so we know that we have a head pointer, which I'm just going to refer to as the head, and we also have our node, which is made up of two components, again, the data and the next pointer, which some people call link. I like to call it next. It just makes more sense to me. And so when we're inserting in the beginning of the linked list, but something is already there, we have to make sure we get the logic right. So right now, if we draw what this is looking like again, in the most basic sense of inserting before something is we have just one node in the list, and that node is currently being pointed by the head. So we have to be careful in the order we do things, otherwise we break it, basically. So the first thing is, in any of these scenarios, is you got to make a node, the new node that you're inserting. So bam, we got a node. We use a constructor to set the pointer to null, so that whenever something is not connected, it's set to null, because it's the sign that we like to use to know that it's not pointing to anything. Or in my drawings, it's just basically a circle. Okay, so what we need to do here, and we need to do it in this order, is, again, this is we're called next, and this is called data. What we need to do is we need to assign the value of next to whatever the value of head is, because this is some address in memory. What we need to do is we need to copy that address here. What that actually does is it makes now this point to that. That's the first step of inserting. The next thing we need to do is we need to update the head pointer. The head pointer is now pointing to the second item in the list, but the head should always point to the first item of the list, which is what we just inserted. So what we need to do is we need to actually overwrite this value with the address of this node. Now, where is the address of that node located? Well, it's a bit of a trick question because I never gave it to you. The point is, at some point in time, you're going to write a piece of code that's going to say node and then some temporary variable, and then you're going to say new node. And of course, we're using templates, so you add your /ds or whatever in here. But you're going to have something like this. Let's say that this is integers and you're inserting a 5 in there. You're going to have some piece of code that says like that. So that means that this node is actually held in temp. So because we have that line of code, we can actually update head with that address, which might be address, I don't know, 500. So what that's going to do is that's going to make this point to the brand new first node. And now we are complete with this. It's 2 lines of code. We're not counting the actual creation of this, because we got to do that for any case. But it's very important that we get them right. If we do them backwards, this whole thing is not going to work. Because if we first overwrite the head, so let me show you what would happen if we did it backwards. If we have our node like this, and we're creating another node, so this is the node that we're making now, and we have head here, and then we got this temp. If we do this backwards, so if first we update head with temp, what we're doing is we're pointing it here by saying head gets temp. Okay, well that takes half of the work done, but here's the thing. We still need to make this point to that. But now we've lost the access to this. We've actually created a memory leak because there's no connection here anymore. And the only way to get to your list is with the head pointer. So you got to be actually always very careful with the head pointer, which is why you always want to make it private. And whenever you're dealing with the head pointer, make a copy of it and work with the copy just to be extra safe. But yeah, in this case, this is why this is basically not going to work. Okay? So order matters when you're dealing with this pointer stuff. Okay, so this is the example of inserting at the beginning of the list. And again, we're going to code this in a minute, but I mean, you can literally see most of the code here already. Let me just move this a little bit down. Okay? The next scenario is again the one where we're inserting at the end. So in the scenario at the end, we have something like this. And we have our head pointer here. First of all, we need to be able to insert at the end, we need to basically get this pointer. That pointer is located in this node. So we need to get the address of that node. But we don't have that address anywhere ready to go. If we had a tail pointer, we would, but we don't. So what we actually need to do is we need to traverse a linked list. Again, this is why linked lists are slow access time. So how do you traverse a linked list? You can do it in 2 ways. One way is you can use recursion, but we're not going to do that right now. We'll do that when we're talking about printing a list. For now, we're going to do it in the other way, which is better, I suppose, because it's less memory. And that's the iterative way, which is with a while loop. I mean, you could use a for loop technically, but I recommend you use a while loop. So with a while loop, what we're going to do is, first of all, we're going to start actually before I preach what you, or do what you preach, right? we're not gonna make sure we're gonna make a temporary pointer. And let's not confuse it with the temporary pointer that I was talking about earlier, because I mean, at the end of the day, like I said, all of these are gonna have this new call, right? Because this is actually what's creating the node. We're spawning a node from nothing, right? So we just spawned our node that we're about to use, and now, as I said, do what you preach or whatever that quote is. Let me make a pointer and copy the head pointer to it. Again, I want to make sure I don't break the head pointer by accident. So the reason I'm doing this is because now I have two pointers. We have cur, which stands for current. It's a very commonly used term, or at least for me in my world. So practice what you preach. There we go. I should write that down. Practice what you preach. So anyways, essentially, we now have two pointers pointing to the first node. Cur is equal to head, so they're both pointing there. Now we're going to manipulate the cur pointer so that we slowly move it to the end of the list so that it's pointing to this node, because that's what we want. Because if it's pointing there, then we can access the next pointer here by saying cur next. Or we could technically access the data if we wanted, like if we were looking for something, by saying cur data, right? So that's why we're making a copy of this, because we don't want to break the head pointer, okay? So that's why we have this line. Okay, so now that we have the cur pointer, what we're going to do is we want to get to the end of the list. And if we coded this right, the end of the list should have the node next pointer always pointing to null, which again is what that little black circle stands for. So right now, if I was to see the next pointer here in that node, it would be equal to null. And that's why that's so important that we do that, because that's how we know that it's think about it like a roadwork sign, okay? Like imagine, I'm sure you've seen it in Hollywood and things like that, like a car jumping up a bridge or something, right? You get the sign that says road closed before the bridge because the bridge is being built or something, right? And so the null pointer is like the sign that says road closed. We've got to make sure we put that sign when we're building the bridge or when we're building these linked lists, because if we don't, we're basically going to drive off the cliff, okay? And we don't want that. We don't want to drive off any cliffs, okay? Not in this class. All right, so I'm very thirsty today. So essentially, because we know that we are good coders and we have created this pointer to null, we have our road close sign, what we can do is we can do a for loop, or sorry, a while loop that says while cur is not equal to null. What that means is that this loop is going to keep running until we hit the null pointer. And if we do that, then essentially you can do whatever you want in this code, but when you hit that road close sign, it's going to get out of the loop. And that can be very, very, very useful, because that can be our way of avoiding basically a segmentation fault, which is the equivalent of driving off the cliff. Okay? But we have a bit of an issue here. First of all, let's see what we need to do to update this. Well, cur is right now pointing to head. So if we say cur is equal to cur next, I want you to see what this line of code is going to do. Cur next right now, because cur is pointing to the first node, cur next is the equivalent of this pointer right here. So that actually gives us access to that node. Yes, you are absolutely correct. In fact, this is the way that we're going to search through the list. It's just that we kind of have to insert stuff to the list so that we can search through it. So that's why we're going over the insert first. But yes, you'll see that searching through a list is super easy using this while loop, because all you have to do is write an if statement in there that says cur data equal to what you're looking for, and you're in business. So anyways, cur next is basically right now the equivalent of this node right here. In fact, if I set cur next data, I'm actually able to get this data right here. Okay? So when I go ahead and say cur gets cur next, what I'm doing is I'm updating the cur pointer one node ahead. So maybe I'm gonna go ahead and do one more node here so you can see it better. So maybe like add one more node, just so you can see the example better. But if we do that, when I say cur gets cur next, I am updating my pointer from pointing to cur on the first node like this to now cur being that right there. That is the effect of this line right here, because cur next again is this pointer here. So I am updating a pointer with cur next as a whole, which as a result makes me point to the next linked list node. Okay? If I do it again, then yet again I would go ahead and go there. And then if I try to do it again, I'm going to see that this is null. And so that's going to make me get out of the loop. But I do have a bit of a problem there. By the time that I get out of the loop, cur is pointing to null. And I actually needed to point to the last node, not to null. So one of the things that I can do to update this is I can change what's inside of the while loop from cur not equal to null to, oh, I forgot to move the exclamation point, to cur next not equal to null. Because now, if I'm pointing at the last node and I can see that the next node is going to be null, then I get out of the loop. And here's the difference. Before, if I was to look at cur outside the loop, it would have been null. I mean, that's why we got out of the loop. But now it's cur next that's null, but cur itself is pointing to the last node, which is exactly what I want. So that's pretty much all it takes. Just this line of code right there. This will basically do what's called traversing, as you pointed out. Or you said search, but traversing, basically walking to the linked list to either search something for it, or in our case, because we just want to get to the end of the list. However, the way I have the code written is a little risky here, because if there's only one node in my list and I try to do cur next, actually no, that would still be okay. The only problem that I would have in this code is if cur was equal to null. Now, why would cur be equal to null? Because head is equal to null, which is basically that the list is empty, right? So how do I fix that issue? Well, I don't have to worry about it, because as you see here, the first thing that we want to check is whether that list is empty or not. And if it is, we would have never called this function to insert at the beginning. We would have just done this mark, which is just basically, actually we haven't done that, but all it is you would just say head gets new node, blah, blah, blah. Single line of code, and you pretty much call it a day there. So essentially, that's the only scenario where this code would be unsafe, if cur was equal to null because head was equal to null. But as long as you do that other check beforehand, then you don't need to worry about this, okay? And I'll show you this in code again in a minute. But anyways, now that we know that we are at this point at the end of the list, with cur pointing to the last node, we just have to insert now. So to insert, we have our temp node, so the temp variable that's holding the node. So all we really got to do is update cur next to be equal to temp. And so that's going to do is, if we say that this is the temp node up here, we are updating cur next, which is this pointer, which is currently pointing to null, and instead we're making it point to that node. So now we're pretty much done. That's all there's to it, a single line of code. But I guess, the loop as well, technically, right? But other than the loop, you need to update just one. You don't need to update head in this scenario because head doesn't need to change. If you had a tail pointer, then that would be a different story. You have to update that as well. But if you had a tail pointer, you wouldn't need to do this while loop in the first place. So yeah, some things become easier with tail pointer at the cost of having to make sure you keep track of the tail pointer being updated, which we'll talk about at the end. Again, I don't want to add more complicated things into this. So that pretty much takes care of inserting in the beginning, inserting at the end, and when you have a list empty, like I said, you just called head equals to the new node. Now all we have left is inserting at the middle. That's a little tricky, because if you're inserting at the middle, the reasons why you typically insert in the middle, by the way, are if you're working with a sorted linked list. And so a sorted linked list is a linked list that is organized by numerical or alphabetical order. So you might have something like 2, 5, and 7, and this is sorted. And then if you want to insert like a 4, then that has to go in between here, right? So that's the scenario where you actually have to insert something in the middle. To insert in the middle, all you really need to do is get the pointer from like the one before you want to insert. So in this case, the 2. If you only get the pointer for the 5, you have a problem, because you actually need to change things in here. And unless it's a double linked list, which we haven't talked about, then you really don't have a way around that. So essentially, what your goal is to get here. Now, how do you get there? The same way as before, with a while loop. And you can use the trick with cur next to make sure you don't skip it. So we're actually going to just copy and paste this code and modify it. Oh, I'm going to zoom out a little bit. Copy. Paste, and let me clean it up. So let's get rid of the linked list drawing. And then let's get rid of this. And let's get rid of that. And that. Okay. So we got our brand new node temp, which we lost. It's LMP now for some reason. And then the parentheses we lost too. Okay, so we got our new node. We're making still another cur, just to make sure we don't break the head, practice what you preach. And then we're going to have the loop, which is going to get us to the point that we need to insert. So it's going to get us to the 2. Now, in this case, the 2 happened to be the first thing. But, to emphasize that doesn't have to be the case, let's just add one more number here. Let's say there's a 1. And we add a head pointer like that. So what we need to do is we need to have the while loop like this. Cur next is not equal to null. But we need to have another scenario to break out of the loop. Now, I could add that scenario here in the actual while loop itself, like here. But I like having this condition here, because it prevents me from running out of that bridge, not seeing the road sign. But you can definitely make it as a composed while statement. Maybe we'll do that when we actually code it. But what you can say is something like if, and you probably want to do that actually before this. You always want to do the cur next thing at the end of your while loop. So if you're doing anything before it, do it here. This should be the last line of your while loop. Okay, it's kind of like if it was a for loop and the I++ happening at the end. This is kind of the equivalent of that, because like we know, make sure we're on the same page here. If I have a for loop that says like for int I is equal to 0, I is less than 5, I++, if I convert this into a while loop, this is basically saying while we have int I equal to 0, while I is less than 5, and then I have my while loop, which at the end of it I have I++, right? That will be the exact conversion from a for loop into a while loop. And all the code that happens inside the while loop has to happen before the I++, right? Think of it that way. Same thing here. This, in fact, you could technically write this like a for loop actually, if you really wanted to. I think it'll let you. You could do something like for, and then put your condition like cur next not equal to 0, or not equal to 0. Sorry. Well, it actually would work, but I prefer null. And then actually that first part of the while loop, the int I equal to 0, we could do something like node cur equal to head. The second part will be this, and then the I++ would actually just be cur equal to cur next. And you could probably overload the post increment operator so that you could just do something like cur++ or something. That'd be pretty cool actually. But yeah, you could do a for loop like this actually, and that would be the exact equivalent of this. I don't think I've ever really done that, but maybe we'll do it just for fun. Copied and pasted that again. But anyways, back to this here. That is indeed a crazy for loop, but I don't know. Some people really like for loops, so You know, if you hate while loops, you can do that. But yeah, okay. So anyways, if we say something like if cur next data, if that is equal to what we're looking for, so like let's say we're trying to insert something that is in the middle, so like greater than what we're looking at but smaller than the next number, then we can say something like if cur data is greater than or less than, yeah, if cur data is less than or equal to what we're trying to currently insert, so like temp data, then break. You can break out of the loop. Like I said, you could put this exact same thing, flip the logic here with the less than or equal to, and you could actually put it in here. But we'll put it there for now, just to make it more clear. So what I'm doing here is I'm saying, okay, when I see the number that follows being small, you know, being smaller than what I'm trying to insert. Actually, do I want it smaller or bigger than? If I'm looking at 2 and the next number to insert is a 5. Yes. Okay, so this is actually correct. Because if that number is smaller, then that means that I need to go after it. Oh, no. The cortex data is bigger. Yeah, bigger. It has to be bigger. Yeah, bigger. So let me flip the logic there. Greater than or equal to. What I'm trying to do with this is I'm trying to say that the next number is bigger than 4. That means that it has to go before it, right? Yes. Because 2 is not bigger than 4, but 5 is bigger than 4. So we want to insert it before 5. So in that scenario, we're basically going to say if cur next data, which is the next number, is bigger than the number we want to insert, that's when we want to insert. Okay, so that's good. So anyways, after this code, cur currently contains the number before we need to insert. So since it contains the number before we need to insert, what we need to do is we need to take this pointer and we need to make it point to the new node that we're inserting. But we can't just do that immediately because then we'll lose links to this part of the list. So the first thing we actually want to do is we want to copy this pointer here, because that's going to make this point here. And then now that we copy that, then go ahead and make it point there, so that now the chain will not be screwed up essentially. Okay. So what that looks like in code is this following. Cur is currently pointing to this. Again, this is a 2 and this is a 5 and this is a 4. Cur is currently pointing to the 2. So we're going to update temp next. Temp is currently pointing to the node that we're trying to insert. So let me draw that. So we got cur pointing to the 2 and temp pointing to the node that we're trying to insert. And right now the pointers are pointing like that. So temp next, which is the purple one, we're going to update that to whatever cur next is currently pointing to, which is the green one. So we do that by literally saying temp next gets cur next. If we do that, we will basically have linked this node, the 4, to go to the 5. So right now it's kind of like a parallel thing. Like we got temp. So if I clean this up, let me clean up this drawing. So right now with that line of code, we have the following. We have this. Okay? That's color coded correctly right there. So we are copying the green line into the purple line. So that way it makes the link to they both point to 5. Next thing we're going to do is we're going to change the green line to point to the red line, which is this one. Okay, so we want to basically overwrite that so that now it points there. Okay, we do that by saying That's a weird C. Cur next is equal to temp. Not temp next, but temp. If we did temp next, we'd essentially be making a point to 5, which will do nothing. Again, you can see how it's, if you know, flipping these two lines will break everything. You don't want to, you want to make sure they don't get flipped. So by doing that, we're basically taking the red one, which is, and then we're taking the green one, and we're basically overriding it with the red. Just like that drawing, okay? It's very important that you follow that. That's it. That takes care of both pointers, and we are good to go. So anyways, that's inserting. So let's go ahead and actually do this in code, which is pretty much this. So for the rest of the lecture, last half an hour, we are just going to code. Need more water. So what you're looking at there is what we did last class. Have we shown the code on deleting an element in the list? Not yet. We haven't shown how to delete yet. We'll do that probably after we finish inserting. Because it's kind of hard to show you the code for delete and then I can't show you it working because we haven't, like, you know, coded a linked list. So the plan is going to be, we're going to code insert, then we're going to code a print, which we'll do even a recursive print, and then we'll do maybe some delete. But we're probably not going to get to delete today. So, I mean, it's not that, it's pretty fast, but, you know, because insert is the hardest function, not because it's the hard in difficulty, but like because it has all of the concepts that you need. If you know how to insert into a linked list, then you know how to delete, and you know how to print, and you know how to do pretty much everything. Because like you need, it's like insert is a combination of all skills. If you know how to do that one, you got it. That's why I basically spent the last, I guess, 50 minutes on insert. Because it really has like everything you need for the linked list. Now it's a matter of just being like, oh, by the way, the same thing we did for insert, we can use for delete. Or the same thing we did for this, we can use for printing. Like the whole traversal thing, like you said, that we can basically search the list is indeed correct. Because it's all in insert, you know. So insert is the most important thing to know. So anyways, this is templated, so this is going to be a headache probably because of the template stuff, but we'll deal with it. But okay, so again, we're going to basically make each function separate. So like insert at start, insert at end, and then insert at middle. But we'll have to either pick an index or do the thing where we're doing with a greater than or less than. We'll have to do something for that one. And then I'll flat out like insert like empty or something. Okay. So let's start with the insert empty. So this function is basically to insert into an empty linked list, which is just as easy as basically saying, okay, head gets whatever we want. So actually, what we're going to do is we're going to have a parameter for all these functions, and that parameter is going to be what we want to insert. So the data component, okay? So the data component is templated, so it's a T, and then the we're going to call that just D for data. And so the first and only thing we're going to do here is we're going to say head gets a new node, and then we're going to pass these to the constructor of that. That will basically make a new node and then put the data into the data component, and will automatically set the next component to null because of the constructor that we did last time. So that's pretty much how you would do that. But I'm going to not keep it inside the function like this because I want to not make the code be super long. So yeah, by the way, I need to put the word void. Otherwise it'll complain. Okay, so what I mean by that is I'm going to write all my functions outside so that I can keep this as tiny as possible. Like that. Now, because now I put it outside, I have to make sure I put the class name, which in this case is linked list, scope resolution operator. But because of how this works, you got to put in here, I believe, that. That's the syntax for that. Oh, I also forgot the word template on the top here. Template. Like I said, this is going to be a headache with the templates, but I kind of want to show you with templates because people in 302 struggle with templates a lot. And I think that's because there's not enough practice on in 202. So I really want to emphasize that to prepare you for 302. So, okay. So anyways, as you can see, it would look so much nicer when it was inside. Like we didn't have to worry about any of this blah and this blah. We just have to like write this code, right? But again, it's good practice. It's good for you. Eat your vegetables kind of thing. All right, so that's the insert empty. That's kind of lame. It's not that exciting. It's only gonna ever be called once, but you know, whatever. All right, let's do another function. This one's gonna be insert at start. That was when we insert the beginning of an existing linked list. And again, the only thing we're passing in is what we're trying to put in, the data component. Okay, so let's go ahead and do that one right here. So, oh, well, that's not what I meant to do. Okay, I'm gonna go ahead and copy and paste this big blob of template stuff so that I can just go ahead and write this. Insert at start, TD for the data. And this time we need a temporary pointer. So we're gonna say node t pointer cur, or temp actually, since we used the word temp before, is equal to, and then the new node line. So new node t with data in it. Okay? The two biggest saying, each of our supposed to write your code definitions of the class. And also don't forget, practice what you preach. And we also have a print function, by the way. So we can actually, here, let's just call the print function right here so that you can see that this is working nice. Okay? That, I mean, we don't have to do this, but I think we're gonna, let's do it in all of these so that we can confirm that things inserted successfully. Okay? So it just calls random print after each insertion. Okay, so that's it. Oh no, that's not it. Lies. We still need to actually put it in the list, right? But the list already has something in it. So if I go ahead and pop open here the iPad, it's this one. Yeah, it's this one, the first one up there. So we need to do that. N is equal to H, and then H is equal to temp. And being the next pointer. So what we're going to do here is we're going to say temp next, which is currently pointing to the next pointer. So actually, let's do the print after we do this line so we can see that address being changed like that. So what we're going to do is we're going to update the next pointer in the new node that we just made. It's currently pointing to null, but it's no longer going to point to null. It's going to point to whatever the head is pointing to because that's the first node of the list, right? So basically what I explained there, just like if you're watching on YouTube, just rewind and re-listen to that part. But yeah, so yeah, that's pretty much it. And then we just need to update the head now to be temp, so that it's all, the head is always pointing to the first node because this one's inserting at the start. The new node that we just made is the one that is going to basically point to head. So this one right here, okay? So we inserted this, so before this was pointing to here, and so what we did is now we make it point here. So first we copy the head to the next pointer, so the next pointing up there. You can't see the line, but it goes like that. And then we update the head to point to the new node. So that's where these two lines come from. Again, we just covered that. Okay, so yeah, even though this doesn't matter, I'm gonna move that down one more time. I want this to be the last thing. So that takes care of inserting at the start. So next, let's go ahead and do the insert at the end. Insert at end. This one's more interesting because we have to traverse the linked list. Why is that? There we go. Okay, color coding. So template class T, void linked list, colon, insert at end, TD. Everything's pretty much the same. What changes is the code inside. But we still need to make a brand new node, so we're just going to copy that over like that. Actually, why is that not tabbed nicely? I don't like this being tabbed like that. But I've been tabbing it. I don't know why I decided to not tab fully. Okay. I know a lot of people like really compressed code. Not a fan of that, so that's why I like my code with like a full tab. But you can do whatever you want. Free country. So anyways, we have a temporary pointer at home. My lips are dry again. More water. All right. I think it's the I turned on the heater to them, so like it's like making the environment really dry. So yeah. Okay. So we got temp with a brand new node, and what we're trying to do is we're trying to insert at the end, and that is you can't really see it here, but it was the while loop that we did. You know, that big while loop there. I'll just kind of leave it like that. Don't worry, I'm about to type the code so you'll see it. But essentially, what we first got to do here is make a temporary pointer. Another one. This one we'll call the curve pointer. By the way, do I need this here? Let me see. See if this compiles without that. I was playing the other day and I didn't need it, so. No, it does say missing tempo argument. Okay. So yeah, okay. I don't know why. Maybe that was I was dreaming or something. But I feel like I was doing some code and I didn't use it and it was compiling. So who knows? Anyways, we're gonna set that to head. So again, we're making sort of a copy of the pointer. That is not something that you should be surprised of. Like, you will dream of code. Trust me, you will dream of code. Like, I've dreamt of code so many times, especially when you're like just working on an assignment or some sort of code, and then you go to sleep immediately after. So you're like, you know, you're working until like 4 a.m. then go to sleep. You're guaranteed going to dream of code. In fact, I would question you if you, by the end of the CS degree, if you have not dreamed in code, then you probably don't remember your dreams. You know, the whole wake up with the solution, I read that online. I've never really had that. I mean, I've had it like, yes, you know, walk away from the code, and then while I'm eating breakfast, like, my mind is clear and I can come up with a solution. But I've never had the thing where like people say like, oh yeah, no, in the dream I saw the solution and I could like figure it out. No, the times that I dreamed in code, it makes no utter sense. It's like, let me do a post increment to fix my sec fault or something, like something completely unrelated. And in the dream it's like, oh, this is such an amazing idea, like this is gonna work great. And then you test it and it works. And then you wake up and you're like, I wasn't even coding in C++. Like, there's no even post increment in Python. So like, where did that even come from? So yeah, I disagree with but I mean, hey, if it works for some people, it works. But I'm pretty good at remembering my dreams. I mean, I post it on Discord all the time. I do not censor my dreams. I will like dream of like weird scenarios, like I'm teaching in class or I'm a student, and like people that are my students, like I see in the dreams, like the TA for Trio 2, right? I had a dream with him. That's I forgot most of the dream at this point, but in the dream it was mentioned that he had a twin, and it turned out to be true. And it's because at some point, very out of context, I didn't put attention to it. It was mentioned by him or by someone, and it was like really back in the mind that I heard it, and it just kind of bounced around for a couple of months and then came back in the dream like that. So yeah, I have the most random dreams with like people, and I just tell them about it. Sometimes they freak out because they think I'm like thinking about them or something. I'm like, no, I'm just telling you, you just came to my dream, and it's not my fault. But yeah. So do not be surprised if like I have random dreams. I have not yet dreamed of teaching, I think, like a live stream. Maybe not. I don't think so. I used to keep a dream diary. That's why I'm very good at remembering dreams. But you do forget them if you don't talk about them. That's why I remember the twin thing, because I talked about it on Discord. But anyways, let's go ahead and finish this since we got 15 minutes. We should be able to finish it. Well, yeah, you're always thinking when you go to sleep, and you can come up with it. What sucks is if you think of a solution and then you go to sleep and then you forget about it. Now that sucks. That's depressing. But, you know, whatever. So anyways, we're going to write a cur loop here that says, well, cur next is not equal to null, which is exactly what we had on paper. So now I'm just basically copying the code into the computer. And then I'm just updating it to say cur next, right? But right beneath it, I'm going to write the equivalent for loop because I want to see if that works. So, yeah, so we'll do like for. We won't even need anything in the body of the loop, actually. I can say node pointer cur. I'll call it cur2 because I'm going to comment out the other one when I test this. That's the first part of the loop. The middle part is the part in loop has a name. You'll learn about it in 326. It's called the loop invariant, I think. Yeah, so that would be basically the for loop. Just like that. There's nothing inside the body in this one. But I'm going to comment it out and we'll test it later and see if it works. All right. Okay. So anyways, this gets us to the end of the list. We just got to call the cur next. Not the end of the list, but the last item in the list. Important difference between that and being null. Because the point is that we want it to be the last item so that we can update that from null to temp. And that's it. That's all there's to it. Let's compile just to make sure it's still okay. And now the only one left is the one in the middle, because we did empty, beginning, and middle. The middle one's, like I said, tricky because normally when you're thinking about inserting in the middle is because it's a sorted linked list. So maybe what we'll do is we'll say insert at, we can say like insert at 5, but the risk of doing that is that we don't know if that's truly in the middle. Could be at the end or the beginning. So I'll just say insert at function. How about that? And what that means is we're going to pass it a pointer. And it's the pointer we want to insert immediately after with the given assumption that it might be in the middle or at the end. Yeah, we'll do that. So that means this one's going to have a pointer in it, which is like pointing to the current node. So we'll call this like cur. And then it's going to have the data that we want to insert as well. Okay, so this one's kind of getting kind of creative. It'll make more sense, this function, when we're actually doing a sorted linked list. That's why right now it's kind of weird. But it's a useful thing to have. Like, I want to insert at the 5th spot in the list. You know, that's a legitimate, like, need. I mean, in fact, I could actually do it as an index here, but I'm using it as a pointer right now. And I'll make the searching at a different function later on, some other day. Now, what you don't want to do is what I just did here, which is give a parameter to one of them and not to the other one. That's not a good habit. You either do give them or don't give them. Don't do like half and half. I don't even know if that'll compile actually. It probably might actually. Cur data template class T node pointer. Oh, that should be outside. Okay. All right. So we are given the assumption that cur contains like the 2 in it, and we want to insert next to it. So that means that cur next is going to have. Well, actually, first of all, before we do any of this, do the same thing the other ones we did, which is let's make our brand new node that we want to insert and copy the data into the data component, which is that line of code. Okay, so now that we did that, we can go ahead and do cur next gets temp. But before we do that, because again, if we do that, we're going to lose the link. So we're going to follow the order here. That order right there, which you can't see, but I'll write it and then you remember. That's temp next gets cur next. We want to do that first, and then we can do cur next gets temp. Now, you'll actually see that this works also in the case of like being at the end, because we're making the assumption that cur next is not given null. And as long as it's not given null, then even if cur next is null, that's okay, because temp next is already null, so it'd just be null equals null. And then cur next being temp, if that was the scenario, then again, we assume that cur is not equal to null. And if you want to be extra safe, you can do that. You can say if cur is not equal to null, or if cur is equal to null, then just return. You know, see out like null pointer exception or something. That's an error check, okay? But anyway, so this code should be relatively safe. I'm going to add my prints, which I forgot to keep adding. So temp gets print and then do print here. Okay, so we finished doing the inserts. So let's go ahead and try it out. Let's make a brand new linked list of integers. Call it L1 or LL1 for linked list 1. Just LL maybe. No, because we might have more than one. Okay. By the way, this class is by no means ready to go because I don't even think. Well, there's memory leaks because we don't have a delete or deallocate yet. So maybe we should add that eventually. Also, if you try to make a copy between these linked lists, it's going to be a shallow copy. It's not going to be a deep copy. We got to figure that out later on. Rule of tree, assignment operator, copy constructor. We gotta do a bunch of work over there. Okay, so by no means is this complete. So our memory is safe. But for the basic stuff that I'm showing you, it'll be okay for now. Don't worry, we will indeed complete it. So let's start inserting. Let's go ahead and insert at empty, because that's the first one we gotta call. Let's insert into that a 6. And then let's insert at start a 8. Then let's go ahead and insert at end. Or actually, let's insert at start again. So maybe a 5. I don't want to put duplicates so that we can see better working. Let's do insert at end, maybe a 1. And then let's try to, you really should test one of these, each of these at a time, frankly, to avoid bad things from happening. But we're going to be confident that we coded it right, which by no means is, I mean, actually, the fact that we did it on paper, there's a high chance that we won't segfault, but still some chance that we will segfault. Let's do the insert at, and in this case, we need to give it a specific node. Well, we can cheat and get the L, we can get the head. Oh, it's private? Yeah, it's private. Okay, so we can't really call that function right now. Let's, just to test it, let's make it public. Let's make the head public. So that we can do something like head next. So that would give us the first node. This would give us the second node. Okay, so we'll give it the second node, and then we're going to insert a, what number have we not done yet? 6? No, we did 6 already, 3. So that should actually insert at between the second and the third node. Because head is the first one, next is the second. Oh, wait, no. Head is the first one, so head next is the second, head, so that's the third node. So it's actually going to insert between the third and fourth node. Maybe we do one more here at the end. Okay, so this should insert between the, like I said, this is first, second, third, between the third and fourth. Okay, so this should be, okay, when we inserted 6, we inserted 6. Then the 8 should go before the 6 because it's inserting as a start. Then the 5 should go before the 8. And then insert at the end, so then you should have a 1. And then a 2. And then the 3 should go, like I said, this is head. This is head next. Head next, next. So it should insert the 3 right there. So that's what we should see at the end. So we're going to call LL1 print, but we don't have a print function yet. So we need to code the print function. Let's code the print function really fast. Otherwise, we won't be able to see anything happening. So we have a print function for the node, but we don't have a print function for the linked list itself. So let's just do that one in line here so we can do it quickly. So for that, as you guys very conveniently mentioned, all we got to do is basically do a for loop. While cur, so first of all, copy a head pointer into a new pointer. So no t pointer cur is equal to head. And then run your for loop by saying, well, cur is not equal to null. This one doesn't need to say cur next. And then inside of the loop here, we can just go ahead and say something like print or cur print. Since we have a print function for the node, we can just call that actually. I don't know if we'll need a line feed. No, it has a line feed of its own, so we'll be okay. We don't need to add an extra line feed. And that's it. Yeah. Oh, wait. We need to do cur equals cur next. Okay. So now we can go ahead and call the print function here. And that should hopefully print out this along with some pointers and other things. But we should see that order happen. If it doesn't, then we will see that things don't work. Line 38. No T temp is new, no T D. I can see that that's not highlighting for some reason. D was not declared in the scope. Oh, I called it data for some reason. There we go. Those memory lists are going to cost me 60%. You know, that's the beauty of it. I already have a PhD, so I don't have to worry about that. All right, so we got a bunch of stuff that printed. Let's see if this is right. That's a lot of numbers. That's not a good sign. Oh, I see why. It's because every time we insert, we're calling the print function. So that's okay. So we're inserting a 6, yes. As you can see, the next pointer is null because it's the only thing in the list. We then go ahead and insert the 8, and we can see that it's pointing to some address, which I'm just going to assume it's the 6's address. Then we insert a 5, which is going to point to what I assume to be the 8's address. We inserted the 1, which is pointing to null as the next address, which is okay because that's inserting at the end, so it should be at the end and point to null. That's the road work sign, so we don't go off the cliff. Same thing with the 2, which then gets inserted at the new end. So it's like, hey, we just made progress on our bridge to pass the class. Okay, so then the rest of these, actually then we got the 3. The 3 is also insertion. And this address is not shown here, but it is the address of the 1. So this 1 is probably this address. Okay, now the rest of these are actually from this print function. You could see that better if I went ahead and added like a line feed here. So as you can see, we indeed have 5, 8, 6, 3, 1, and 2. So yeah, it works perfect. Yay. If it didn't, we only have 2 minutes to debug it. But just so you can see those nasty memory leaks, we do indeed have a memory leaks indeed, which come from, of course, the fact that we haven't deallocated it. We don't have any errors, but we have memory leaks. So the way we have to fix this is we have to add a destructor at the very least. So we can do that in 2 minutes, even if we don't, I can explain it later on. But since you guys are basically challenging me into doing this, then I'll go ahead and do it. So linked list. The destructor is actually very similar to the print function. All you gotta do is basically walk around with this. So this time around, I don't need to worry about the head pointer, so I can actually manipulate it directly. I could make a temporary pointer, extra line of code, don't have the time for that. So I can just go ahead and say, while head is not equal to null, head is equal to head next. And then I do need a temporary pointer if I want to do this the right way, actually. I'll talk about that next time. But reason being is because I have to do delete temp after that. Otherwise, I am accessing a dangling pointer technically. So, yep, that's it. If I do that, I have no longer any memory leaks. So there we go, my grade has passed. Basically, it's just a modification of the printing, with the exception being that I make a copy of the pointer of the node that I'm looking at, the pointers to that node, then I traverse to update to the next node, and then I delete it. The naive thing is to actually go ahead and call delete head in this line right here. So basically delete head and then do head next. The reason that's bad is because after I deleted a pointer, I'm accessing it, which is technically accessing a dangling pointer. Can lead to bad situations. Probably won't, but technically can, so it's not a good idea. I'll talk more about how I did this next time. But yeah, no, it's the reason why this says it's still reachable is because of the Iostream library. That's normal for you to see this. If you Google that, that is the Iostream library. If I do this on like a Hello World program, which is like the LL3, I will still see they're still reachable. LL3 is just a hello, not even Hello World, it's just main. So yes, don't panic about that. I believe that that's because I have an outdated version of Valgrind. They fixed that in the latest version of Valgrind, so you shouldn't see that happen on yours. But yeah, that's it. So in review, today we learned how to insert into a linked list. The reason why I spent so long on that is because that is basically the heart of the linked list. If you know how to insert, you know how to do every other operation. Now it's just a matter of tweaking it. Next time, after the test, we will come back and talk about the allocating from the linked list, like I said, with the destructor that I just did. But beyond that, we're also going to talk about deleting specific values of a linked list and how to do that. Searching through a linked list. We'll do a sorted linked list. We're going to do a lot of modifications to this to basically make it a really nice linked list class. Still a lot of work to do, but I think you got the most basics of it, which is making the linked list. Because once you do that, then you can actually start exploring. So, yeah. Like I said, test is next week. Prepare yourselves for that. Get your assignments done. And we shall meet soon. Would the destructor still work after we implement the deep copy in the assignment operator? Doesn't the destructor rely on temp getting a shallow copy of head? So that's not a problem there because we do just want a pointer to head. What we're going to fix with the assignment operator in the linked list class, you see there's two things. One of them is the class for the pointer, so the node class, and the other one is the linked list class. The node class is actually pretty good to go. I mean, yeah, I guess if we try to assign a node to the node, that would make a shallow copy. But that's okay. We want a shallow copy because we want just a pointer to it so that we can actually delete those pointers later on and not a copy of them. So what we need to overload is for when you copy an entire list to another one. So if I say like linked list 1 gets linked list 2, that's just going to copy the head pointer. So now you're going to have two head pointers pointing to the same list, which can be bad because when the destructor gets called, it's going to try to delete the same list twice. So that's going to segfault. So right now, if I added in my code like LL1 equal LL2, I would get a segfault essentially. Are we still going to have 11 total assignments? I guess. I haven't heard any updates, but we'll see, I suppose. I don't know. I do know for a fact that you're going to have a final project because that's required. But, I mean, technically speaking, the only assignments left, I believe, are the linked list assignments, right? And the recursion ones. I don't know if the recursion one has been posted or not. But, yeah, so... yeah, I don't see any changes right now. But as you can see, one of the assignments was worth like 50 points, so that was pretty much not worth a lot. So you could have skipped that one for all I cared. So yeah, like every assignment is worth 300 points, and one of them was 50. So hopefully you guys noticed that. Otherwise, you're like, oh no, I was really hoping more people would do the creepy assignments, but I actually found out the majority of them were from 302. Not from 202, but we still had some people do it actually. So yeah, all right then. Like I said, there is no live stream on Wednesday because of Veterans Day, so there will be no live stream. So hopefully you don't forget and then show up. And if you do, it's not like you go to school. You just close your browser again. Yeah, or 80 points instead of 50. Maybe that's what I meant. But yeah, which is a fraction, really small fraction compared to the other ones. Okay then, so use the time wisely to prepare for the test, and I'll see you guys in a week. So have a good weekend, I guess. Have a good week and a good weekend. So see you guys later and stay in touch. All right, bye.